Okay, we are live. Today we're going to be going through some just airflow basics and how it relates to a refrigeration system, or more specifically, like split systems, RTUs, some of our light commercial side, and even into kind of, I guess, our mid-zone. A lot of these systems are function the same way. I'm not going to dive into the heavier side where we start getting into more of the refined, like static control and constant volume versus variable volume systems. That is going to be for our next class. So this is going to be just a hard set hour-ish. It's not going to be any longer than 1 o'clock. So despite where I'm at, I'm going to be cutting it off at 1 p.m. So everybody's aware. Our team, APS guys, we do have our separate service chat. So please be sure to get in on that. If you have any specific questions or anything, we've got somebody monitoring that and is going to be able to get that into the conversation for you. Everybody else is free to use the YouTube chat outside of that, but just bear in mind that our team, we've got something specific for y'all. Moving beyond that, hello everybody. Hope you're doing well. Hope you're having a good day. This is a temporary, we're kind of experimenting. So historically, we've done these after hours. This is our first one, is just pure webinar style, to be honest. So we're going to see how this goes. We're experimenting a little bit. Our team, I'd love some feedback from y'all on what y'all think about this and trying to do this over your lunch break. We are trying to work out a more long-term plan and bring these during hours instead of everything having to be after hours all the time. Anyway, from there, let's dive into our subjects. So well, I do want to make a distinction, and I talked about right there out the gate, RTUs and splits versus some of our larger systems like a self-contained or like an IntelliPack or a 50N series for a carrier RTU, something along those lines, even a Voyager for that matter. Those would be what I would consider a high static system. Now, I do want to clarify, I'm speaking in a very narrow field of view. When I say high static, it's not what the industry like if you talk to an engineer and you said, hey, we're working on a high static system, what I'm saying right now and what he's going to feed back to you is not actually the same. There are legitimate industry high static systems are 2, 3, 4 inches of static, and they can get real specialized, and the industrial side of things uses a lot of that. When I'm in the moment right now, when I'm making a difference between a high static and a low static system, I'm making a separation between the large commercial systems run, 1 inch of static on the supply side of the duct. And we have a really high external static compared to like an RTU, for example. So RTUs and the regular split systems, we might have an external static. That means between supply and return of, half an inch if we're doing good, right? Or even as low as 0.2 inches of water column and static. So that's my difference here, and that's what I'm separating. So I'm going to hone in on what we would consider for our team a low static system, and the next class will be more focused around the high static side. So with that distinction being in place, I do want to make it clear that airflow is a really critical part of everything that we do. And I've talked about this fairly heavily, but it's not that complicated. I know it feels that way, and when we deal with systems that we struggle understanding because they can be a little bit abstract, which airflow can be. It can have a lot of abstract properties to it. It can be harder to get our minds around, especially because we're very practical people. But end of the day, I want you to think about airflow in just terms of heat. And that's really what it boils down to, and why flow even matters to anything in our system. It's revolving around, it's the amount of heat we're putting in. And so CFM stands for a cubic feet per minute. It's a measurement of how much air, the actual volume of air that's physically moving. So on a RTU, we may be moving 2,000 or 10,000 CFM, depending on the general size of it, whether we're talking a 5-ton RTU or we're talking a 20, 30, 40 ton. And most of the time, those would be considered a constant volume, and we don't need to dive into the variable side today. But what we're achieving is we're just trying to get a certain amount of heat through our coil. And we need to supply our coil with a certain amount of heat so that our refrigerant system can respond the way we want it to. Because when we walk up to a system and we're starting to do a troubleshoot, what we're really honing in on is what is our refrigerant doing? Like from a technician's perspective, not from a design, but from a technician. You walk up, okay, it's not cooling. Why is it not cooling? I'm going to start taking readings, and I'm going to see what those readings translate as. So as I'm looking through the readings, just one variable that is affecting those readings, especially on the evaporator side, is how many CFM are we moving? Because it may not even be that we have a low return. I mean, obviously we're there because it's not cooling, so you would expect that the return air would be elevated, to whatever degree that fit the space. Maybe 75 elevated, maybe 78, maybe 80, could be beyond that. So we're expecting to have a higher load to begin with at this stage. But yet our readings are still showing, like our refrigerants, superheat, saturation on the evap are still showing low on both ends of that spectrum, for example. That we can identify the fact that, okay, we know from a procedural, we're just not moving enough air. What it really means is we're not putting enough heat into the coil. So that is where the air side of our system really starts to integrate and become so vital to the overall function of the refrigerant side. And something I'm really trying to get across to everybody is I really encourage you to start to understand the air side better, because you're going to start to hit a time where you're not going to be able to grasp and dive in and understand the refrigerant side in an advanced way, because you lack understanding of how the air is moving through the system. And I could get off on a whole tangent with psychrometrics and stuff, and we don't need to do that. But the point is, it's how much heat are we actually pushing through there? And that is where it's really going to start to matter. Let me silence that. So how do we measure the air? There's a handful of ways. So CFM is one. So CFM is as I've already explained, it's a way to measure the physical volume. We can use static to also measure air, but it's a different type of measurement. It's about how is the fan responding to the design or the duct system itself, and what's happening with the way the system is functioning. So that is where static plays a big role. And you have a thing called total static. Then you have velocity pressure, you have total pressure, velocity pressure, and then static pressure. Now we commonly talk about the static pressure side, and actually I'm realizing I meant to get a manometer, and I didn't do that. Anyway, we talk about the static side, but static is actually only one of 3 total readings that we can use on a given system. Now, I don't want this to be overcomplicated. So we're going to hone in on the static piece, but I want you to know that the others exist, and the others will become more important in the later classes. But essentially, total static is, so total pressure, I keep saying static. Total pressure is velocity pressure plus static pressure. And we're all familiar with pitot tubes, or at least we should be. If you don't know, a pitot tube is, you'll see them a lot. You can buy them in a lot of your airflow kits. You got like a big magnet over here that'll stick to the unit. You'll have a piece of tubing. A lot of times there'll be aluminum or that'll stick into like a 1/4 inch, 3/8 hole into the side of the system. And then it's got a series of little holes in it. And so those holes will typically only be on one side of the pitot tube, or they'll be down here in the tip of the probe. And you may even have like an airflow indicator back here where the magnet is, and you'll have a tube coming out of this over to a manometer giving you a reading. And so what you're trying to do here is you can read two of these pressures with it. The one we really care about is static pressure in today's conversation. So what's important is, how do we get one from the other? We have to measure static by reading away from the airflow. So in this particular case, let's say that our pickup point was down here in the tip. So this is where we've got a hole. That hole is allowing air pressure to push and pressurize this little tube, and that comes through the nylon tubing that feeds to our meter, and our meter is able to take an actual measurement. So for static is think of it as the outward pressure, okay? When you think of refrigerant pressure, the refrigerant is balled up in a confined space, and it's trying to push out. And it's doing the same thing inside of the ductwork. So your static pressure is the pressure of the air trying to push out or pull in if it's in regards to return. So a return side would have a negative pressure, where the supply side would have a positive pressure. So your airflow in this case would be this direction. So if this was sitting, I technically drew that backwards, didn't I? If this was sitting in an airstream, let's say this was a piece of a duct, it's flowing, you want to read this side, because this side, if you point it towards the airstream, then you're going to get what's known as total pressure, with the probe facing into the air. With it facing away from the air is where you get your static pressure. Now, you'll notice the formula up here looks kind of funky right now, because I told you total, which is on the equal side, and I told you static. Again, I'm going to cover this in a later class. We're not going to spend much time on this. My point is, I want you to understand how to use your tool properly. If you're going to use a pitot pickup in order to read static pressure, you don't have to get a digital manometer. My very first one was a MagnaHelix. MagnaHelix are super effective, but they come with their challenges. So with a MagnaHelix, they're very positional, and there's a lot of things you have to calibrate them. It takes some technical skill when you first try to start to use them. Manometers, digital manometers especially, have really simplified this process for us, to where they self-calibrate, and they do a lot of things for us and make it simple. Anyway, make sure you're facing away you're facing with the airstream with your probe sticking in. I actually made my own of these. My very first, actually I still use them, to be honest. I just took some 1/4-inch aluminum tubing, and I don't have a magnet or anything, so I have to hold it by hand, and I have to I know my tools, so I know how to use it, but I just put a 90-degree bend in some aluminum tubing, some 1/4-inch aluminum tubing. I picked it up off of a job site. It was just some scrap laying on the floor, and I turned that into pickup tubes. And so that's what I use. You don't have to spend money if you ain't got money in order to take these measurements. You can create this stuff yourself. You do also have a hot wire anemometer, which gets you into FPM, which is feet per minute, but that's a different measurement, and it's not velocity, and it's also not pressure. That's like that is like the miles per hour on your car, right? Whether you're driving 5 miles an hour or 60 miles an hour, well, the feet per minute is your speedometer. Think of it like that. Where static really becomes useful on these smaller systems, and not every unit will have this, but a lot of them will. They'll have a external static chart. And I've actually got one. We'll talk through that, and I'll explain that a little more. But external static is a tremendously useful tool on smaller units when you need to do a quick measurement to find out what your CFM is. And like I said, most smaller systems have some form of external static chart. What you do have to be careful with is where are they wanting you to take those measurements. And so on some systems, you take it across the coil. On a lot of systems, you take it across the whole unit. So you actually take the supply side pressure and the return side pressure with the coil and the blower in between. There are some of them, I guess that would be, what am I saying? Let me back up there. We're talking external static, so that would be your external static. There are some units you'll have a pressure drop chart for just the coil. For example, when you're doing a furnace system, a lot of times, of course it's been a while now, I'm sitting here thinking about it since I've done one, the coil itself is a separate component from the actual furnace, and so you can actually just change out just the coil. At that point, you would have a coil pressure drop, and that could help you calculate via the chart what your flow is through that coil. In our particular case, I'm just going to keep it simple with most of the time you're going to have external static as an option, especially working in the commercial space like we do, because we don't run into that many just regular furnaces sitting on the floor or hanging in the, we have them, just it's not as common. A lot of times we have a lot of RTUs. So that's your three main methods or types of ways to measure airflow is through the CFM, your static, and then your feet per minute. Now with feet per minute, that gets into more calculations, and honestly, in my opinion, I don't find it where we have to use it that much. It's usually kind of, because of the extra measurements and the time it takes to do it, I found in my experience that I rarely ever used that method. But if you say you had a system that did not have an external static chart and you needed to measure CFM on it, then you would take the whether this would be the return duct or at the face of the coil, but you would essentially create little zones. Let's say this was a return duct. You would create little zones, and you would need to take multiple measurements across that duct, depending on how big it is. Now, what I'm drawing would be a larger one. Some cases, you may get away with 9 readings. In a larger case, every couple of feet, you would need to be taking a FPM. And so you end up having to do a area calculation, and that area calculation built into your FPM through there, and that FPM is going to change. And so what you're looking for is the average. So you have to take FPM all the way across, because the FPM on the edges is going to be lower than in the middle. And so you have to average it, because if you just take it in the middle, you'll actually end up getting a higher reading than you're actually moving, and so it's not as accurate. So that's what you have to be careful with. Anyway, this is a more in-depth method that is something to have in the toolbox, not something to use very often. We can move on from that. So, external static. We've talked about that. That is going to match. Let me add this to the stream. Bingo, there we go. See, we don't need to see me. Get me out the way. Okay. Hopefully y'all can see that, or it's coming through big enough. I can try to make it bigger. It looks like it may be a little small on y'all's side. So let me do this. Okay, this gets our point across. Hopefully that's easier to see. So with external static, as I said, we're going to take a reading from the return before the evaporator, and we're going to take a reading from the supply side after the fan, or just outside of the unit. So if this was a split system, for example, You know, you wouldn't stick it into where, like, say, the electric heaters were on a heat pump or whatever. You would just get into the supply duct, tap in there, take your reading. And you're taking the difference of that reading. So you might have 0.2 on the supply and 0.2 on the return, and then you would add those together. That's your difference, and that'd give you a 0.4. So looking at this chart, let's pick the 2-ton option there, the second one down. We can see that our CFM is on top. Our watts is what the motor should be pulling, and so that would be, you'd have to calculate that, but that would be for this specific unit. These are not generic charts. I need to preface with that. You cannot just go pull a chart from any system and it's going to serve your function. You need to go find the specific chart for the unit, because an engineer sits here, has to go in, test, and design all these readings. So if we had, so we were at 0.4, right? So if we're looking at our external static pressure on the very top column up there, and you'll see below that you've got 5 different reading options. You have a 0.1, 0.3, 0.5, 0.7, or 0.9. Now to the far right is a whole nother section of the chart, so we're only going to focus in on the left side here. So we have a 2-ton system, and ours is 0.4. Well, that puts us between the 0.3 and 0.5. And essentially, you see there's not a whole lot of difference between them. And let's say we're going to move 400 CFM per ton. So the cooling airflow setting, we've got the unit set. We want 400 a ton. So that's the third option down in the 200 tons options. So that basically means we're somewhere between 820 and 832 CFM. So the 0.4, I mean, so what? You're running 828, okay? That's where this chart becomes very useful, because you can see how much air you're actually moving, and it can help you explain what's going on. Now, one thing I will say is that's if you wanted to find out the CFM. And I talked about the fact that I really want to make this simple. Most of the time, unless you're trying to balance something or achieve a very specific goal, there is, you have to be careful with rule of thumbs, but there is a little bit of a rule of thumb with these types, with low static, as I'm calling them, systems. And that is, you should, like, a healthy system is going to run below 1/2 inch of static. And there are new standards coming out, and I need to preface with that too, because we have to be careful with some of these new standards. We're going to find ourselves having to maintain lower external statics from what I've seen, and it looks like it's coming down. So, right, you know, with older systems, might have gotten away with 0.5 external static. And some of these newer systems, 0.5 probably isn't going to cut it. And we need to get that down even further to, I think, like a 0.2 or 0.3 in a lot of those cases. It's not something I'm completely read up on, but it is something I'm trying to pay attention to. Anyway, the point is, you can use just that external static to give you a general idea of how your airflow is doing. Because if you walk up to a system and you're only running, or you are running a, let's say a 0.9, so we'll come back over to the chart. What happens when we ran a 0.9? Well, a 0.9 meant we went to running 827, if I read this right. Yeah, 827. Versus on the other end, where with a 0.1, it could be reading 799. Now, as I'm looking at this, I think this may be for an ECM. Yeah, because our wattage changes pretty dramatically. So this looks like an ECM style system. So we can get into that in a bit. But typically, a 0.9 would be considered a highly restricted system, and it's going to be struggling with airflow. As a general rule, where a 0.1 would be a system that has really good airflow, Now, that doesn't mean that the ductwork's okay. You know, maybe the supply side's blown out somewhere and it's dumping a bunch of air. So those, you have to take these things into the bigger picture. But my point, it is better to see a lower external static than higher. And if you walk up and you see that your evap saturation and your superheat are already struggling, and because they're low, and then you take a quick external static, which once you get familiar with it, it takes minutes to do. It's not a complicated procedure. Then you would end up being able to quickly identify that, okay, I have an airflow problem, and that explains why I'm having these readings. And you can eliminate a lot of other things that you have to troubleshoot. And that's as part of the point of taking a lot of readings. And it's something where there is a philosophy to this of, you know, how many readings do you spend the time taking versus starting to do more in-depth troubleshooting? And there is a difference because we can troubleshoot a lot of things without taking a lot of extra readings. So in my personal opinion is there are a lot of readings that make a lot of sense. For example, if I see that there's a question on the airflow side, as soon as I hook up and I get my superheats, or my superheat, my subcool, and my saturations, you know, that's one of the very first things a lot of us do. As soon as I get that and I see those lower readings, my first go-to is I'm going to verify what's my airflow look like. And external static is a quick method of accomplishing that. You know, you could also have it with load. You know, you may have a lower load issue in a completely different scenario. And from there, you know, I might want to take a relative humidity and a dry bulb reading of my return, right? Or just a temperature and a humidity reading. That way I can get a good picture of what does my return load actually look like. So those are some just quick readings that really narrow down the list of things that could be giving you problems. And a lot of the time it is in the air side of the system is a root of a lot of problems we have in systems. But I don't feel like a lot of guys pay enough attention to that piece of it because it's not, again, it's abstract, or it can be, and it's not something that we're taught as heavily to practice up front. So I guess that's one of the things I hope to fix here. So, okay, we talked about external static. There's another method of measuring this, and it's a fairly controversial one with the customer during the summertime, and that is the heat rise. So if you really need to know what your CFM is, not, you know, and not just a general, okay, I know what my external static is, that kind of gives me some directive to go off of. No, I need to actually calculate my CFM, but I don't have a external static option. Like that's not on the table. That's okay. There's a couple of quick things you can do, but they involve the heating side. Now in the wintertime, this ain't no big deal, right? You know, we want heat anyway. Once you get practiced at doing this method, it doesn't actually take that long. So it just, the first few times you're going to do it, it may take you longer. You know, when I say longer, so I could walk up and take these readings and have a value within less than 10 minutes at minimum, but usually within 5 minutes of needing to get this number, right? So it's a fairly minimal runtime, and in the big scheme of things, it's not going to have that much impact, in my opinion. Your first couple of times may take you 15, 20 minutes to make sure you got it correct and you're not second guessing yourself. So just be prepared for that. I would really encourage you to practice this when you can. Ultimately, CFM equals BTUs divided by your temperature differential times 1.08. Now, I'm going to specify with these parentheses here. You have to do this calculation first before you divide it into the BTU. So TD, temperature differential, that would be differential across the heater. So basically just between supply and return, right? You got your supply temp, you got your return temp, take the difference, multiply that by what's known as a coefficient. So 1.08 is the coefficient for the formula. Doesn't matter what a coefficient is, that's just the number you use. Then you would divide that into your BTUs. That's grand, fine, awesome. I've got electric heaters. What BTUs does that mean? That's okay. Furnaces have BTUs listed on them if you're not familiar with that. I'm pretty sure most of you should. Ultimately, with electric heat, you just take and you have to get watts first. So it's just your amps. You would just take a amp reading on the heaters. You multiply that by your physical volts, and that's going to give you your watts. And then watts multiplied by 3.414, which is the conversion. So for every watt of energy used, we have 3.4 BTUs worth of heat in that watt. And that would give you your BTUs. Okay, I want to preface this. You need, obviously, amps, you have to take with it running. It's kind of hard to get amps without it running, right? So you have to do that, but don't make the mistake of taking voltage with it off. And also don't make the mistake of using the data tag voltage either. Because if you're going this deep, if you need to get this number for whatever reason, maybe you're commissioning. So that would be a real justification for trying to get this number. I need to commission this system or verify commission, whatever. Then you want to take the voltage reading while the heat is going. So take them both simultaneously and plug that into your calculation. Because you'll notice that you'll turn on all those electric heaters, and then all of a sudden your voltage will drop by several volts. You know, that's pretty common to have happen. So the point is you're going this deep because you need accuracy. This is going to be what makes you the most accurate. In some cases, we have units that are rated for 460 on the data tag, but we've actually feeding it 480, 490. That's going to affect this reading if you try to use the data tag voltage as your calculation. So anyway, that's heat rise. And this will give you CFM. If you need it, if you didn't know what that was, if you didn't know how to do it, you do now. Use it accordingly. So how are we doing on questions? We had anything?
You know, there's been a few good questions, but the chat team, the group's really been helping each other out. I think one that kind of stands out here is density, wet and dry coils, and how that affects your readings.
Between a wet and a dry coil?
Wet, dry coil, yeah. And airflow density.
Yeah, so density is going to go back to the heat that's in the air. Now, heat includes humidity. So if you're only looking at a temperature reading for the dry bulb, then you're only looking at a part of the equation. And so something I want you to understand, you know, we start talking, you know, this is psychrometrics. Leave the rest of the psychrometrics out of it, in my opinion. You know, because we overcomplicate it. So let's really break it down to the nuts and bolts to what you're going to use on a daily basis. That is relative humidity, and that is your dry bulb. Relative humidity is, in my opinion, once you get comfortable with it, it's pretty straightforward. Is it 50%, 60%, 80%, 2%? So that will dictate what your actual humidity or your density. So sure, density has a place, has a part. Is that an active part of our everyday stuff? Because that's something I want to be real clear about here. You know, we could dive into the weeds. I do it all the time. I'm terrible about this. Diving way too far into those weeds, and you get down a rabbit trail that just, what was the real purpose to benefiting the job? All right, I have to rein myself in all the time because of this. So one of the things I'm really trying to do myself and then get better at in presenting these things, what is the actual nuts and bolts that's going to benefit you on a day-to-day? Worrying about density, in my opinion, is not going to have that big of an impact. But there was another part of that question, which was what? So it was density and what?
It was the wet or dry evaporator.
Yes, wet and dry evaporator. That is going to have an impact, right? And it's something, again, you have to take that into account. And that's one of the problems with the heat rise method is very likely that you end up drying your coil out. So a wet coil, you know, it's that condensate is going to restrict in its own right. And that's that's something you just have to be aware of. And that's one of the fallacies of that method, depending on how accurate you're trying to be and what you're trying to do with it. But I come back to what is practical, okay? The CFM that changes between it being wet and dry, is that CFM enough to change your mind on what's happening? And that's the question I want to pose. Is that question appropriate, or is it too deep? Right? And that's an open question. I would love to see some conversation start around that. Is where's that dividing line? Because at some point, and this is a learning thing for me. I'm realizing we got to draw a line here between practical and impractical, and I can admit to I've got some struggles there myself. I'm having to learn this. Any other questions standing out? No? All right. I haven't been watching the chat over here on the YouTube side too much, guys, so I apologize, but it looks like y'all are doing a fantastic job working through some stuff. So all you guys that are in there helping out with that, I appreciate it. All right. Airflow. So some general things on how your airflow is going to impact your refrigerant side. It's going to impact it you're going to see it the most in your evaporator. Now, keep in mind, your condenser is dependent on your evaporator load. So now there's other things that affect a condenser, such as, is it dirty? Is the fan having a problem? You know, there's physical attributes for the condenser that can affect the head pressure, the subcooling, things of that nature. But on a fundamental level, let's say those things were not problems, or you got to the site and you confirm fan's working great, cool's perfectly clean. So that's not part of your problem, right? So in that situation, if you've got low airflow, that's the same thing as just low load, because it's the amount of heat we're giving to the evaporator. So because we're giving the evaporator less heat, we're going to see lower readings in the evaporator. So your saturation and superheat will both be low, or technically could be normal. So it's not uncommon that the TXV has the ability to catch that. So something about TXVs, if you don't know, they have, especially Sporlan ones, I think it's across the board, they have the ability to they derate themselves as much as 30%, a lot of them, not all of them. And that's not a hard set number, but 30% is an average. So if that TXV is rated at, say, 10 tons, well, 30% of that, don't ask me what that is, but 30% of that is how low it can go and hold that refrigerant back without losing control of the superheat. Meaning, in a low airflow scenario, you would end up flooding. So yes, you could walk up and you have a low airflow condition, and that's causing a low saturation. Let's say 35, 34 degrees, maybe even lower Fahrenheit. And so at that stage, your first thought is, okay, well, if you're walking up to troubleshoot, you're going to see the low saturation, but you might see my superheat still 10 degrees or 15 degrees, right? And that in your mind, that's going to cause a conflict, because if you only learn procedures and you don't understand what's actually happening, then you may void your troubleshooting thought about, well, maybe it's airflow, strictly because your superheat looks okay. Well, be careful with that. Don't let that catch you. That may be just because you got a good TXV in the system and it's doing its job. So my point there is to give an example of what you might see. Same thing you go the other way, where we're moving too much air. We're flying it through that coil. That's going to cause its own issues. So, for example, condensation wicking off the coil. Can be a big issue for you, especially on a draw-through coil, which RTUs and a lot of, basically most of what we work on are draw-through evaporators. So you could wick. And so if you open a panel and the whole inside of it's wet, it may not be a leak in the pan. You may just be sucking that condensate straight off of the coil, and it's not making it into the pan when it goes to drip down. So that's one consequence. Another would be elevated saturation and superheat. So you may end up pushing so much air through that coil that the TXV has a hard time feeding enough refrigerant to it. And it could, if you're not, so it's an example of this, you may be running mid to upper 40s on your saturation, but your superheat may be pushing 20 plus, which for me, that's a bad thing. So because of your airflow, even though you're there's people that it would be easy to overlook the saturation and just see high superheat and say, okay, I want to get that superheat down. Why is the superheat so high? And you may not always correlate that the superheat and saturation are high together. So if you're honing in on just the superheat side of it, that would be a really easy road to end up diagnosing a bad TXV. And we all get into blaming metering valves all the time. So they got that whole genre to it, but that's something you have to be careful with. So both of those elevated together are going to cause a symptom like that, basically, is my point. You cut the airflow down, however you throttle it, then you end up seeing the superheat and the saturation come down together. And then the TXV gets to where it actually has throttling range, to where it can control the flow again, because what that high airflow did is it pushed the TXV so far that all it could do is open wide open and flow its maximum value. And it still wasn't enough because you're inputting so much heat. You're also going to see in that situation, because again, the more heat we put into the evaporator, the more heat we have to reject at the condenser. So at the condenser, you're going to see more elevated condenser saturation. You're also going to see higher subcooling values, because it has to throw more heat out in order to maintain the system. So these things are linked together. The condenser is only responding to what the evaporator is inputting into it. Its job is to output. The evaporator's job is to input. You can only output what you're inputting. Anyway, let's see, some other high flow. I think we can move on from that. We're starting to push our time. If you have any questions so far, APS team especially, start hitting those in there before we get to the final stages here. I do want to talk about adjustable pulleys, or having just pulleys in a system. We see this not only in splits, water source heat pumps. The water source heat pumps are going to run off the same, like that's a low static. The RTUs and such. So they come with adjustable pulleys on the motor most of the time. And those usually those will come set all the way out. And you're supposed to, upon installing it, thread those in and set them where they're meant to be. So, and I've gone through a lot of buildings where whoever went through and commissioned the building never set those. And what it ended up leading to is they had a lot of problems because none of the units were moving enough air, because the smaller you make that drive pulley, the slower everything's going to move. And there's a really amazing tool here I will share with you. One second, everybody. So this is layer.com, pulley/belting. So this is a really incredible tool if you're working on a system. You can do a lot of things with it. What I want to represent is, in most cases, our smaller pulley is our smaller pulley is our drive, and our motor pulley, and our fan drive pulley is going to be the larger one typically. And these things, like, if I try to sort this out in my head, I will quickly confuse myself to what's actually happening. So I would recommend having a tool like this because it can really help you determine. So something I want to point out is, if you look at both of the pulleys, and just below them in red lettering, you see RPM. All the other numbers, just don't worry about those right now. Let's focus on just the RPM. Now, I have it set to where the small pulley has read 1750 on the RPM. That's a very typical motor we see on our side, either 1750 or I think 850, I think is an alternative. Anyway, 1750 is the most common. So that's going to be a set speed at that motor. And if we increase our diameter here on that, you'll see that the increase is happening at the larger pulley as well. So you can use a tool like this to help you identify how much do you thread that adjustable pulley in or out. And that's really what you're trying to hone in on. And you can use external static. You can use heat rise method. If you walk up to a system and you see that the adjustable pulley is sitting at its bare minimum, like the thing's wide open, it's very likely that it wasn't adjusted. And vice versa, they're not meant to be all the way in by default either. So that's the two things that I see most common. They will either be all the way adjusted in, or they'll be all the way adjusted out. And that typically, most of those systems where I run the math on what's happening here, I find that it's too far one way or the other. And somebody just didn't take the time to properly commission that pulley and that fan system, and they're not moving the correct airflow to get the most out of it. Because another huge symptom to too much airflow would be high humidity. And that's a lot of times where those calls come from. They come from high humidity in the space. And that high, Jason here says Browning has an app as well. So I wasn't aware of that. That'd be a really great way of doing that. Anyway, we get a call for really high humidity. It feels sticky. It's uncomfortable. We're at set point. We're satisfying set point, and heck, we got it turned down to 70 degrees. It's still uncomfortable. What the heck's going on here? Well, that's a high humidity call, typically. So that is very likely you're moving way too much air. You need to slow that air down, and that's somebody that just rammed that adjustable pulley the wrong direction. And same thing on the low airflow side. We can remove too much humidity, and people can have a lot of sinus issues, and they can have a lot of it leads to other health problems because the air is so dry. It dries out their skin. Everything's uncomfortable just in the other direction. And so they run really high thermostat settings because they're trying to be comfortable, and they're trying to fix a humidity problem by changing the dry bulb. That's all the thermostat's really doing. Anyway, please use tools like that. There's lots of resources out there, and that's really gonna don't walk away from this and try to adjust your whole process overnight. What you should do is take everything I've said, maybe watch this a couple of times over, and take each piece of what I talked about along the way that you're not already familiar with. Okay, anything I've said throughout a class like this, and then take that one piece of it and start to try to apply that one piece of it. For example, the belt piece, or take just understanding external static. Just start taking external static readings as part of your troubleshooting process. And do that one thing, just the one. And as you develop and mature in these skills and you get comfortable with them, then you can start taking some of the other things I've talked about and slowly working that into your process. Because I can tell you that if you try to take everything I've talked about here that you may not practice, which part of my goal is, you should practice all of it, but you're likely practicing very little of what I've talked about. And that's okay up to a certain point. But if you try to take too many of these things, you will overwhelm yourself. You're going to feel like you're struggling to be good enough to understand it and what's happening. And then you're going to, you're likely to give up. And I don't want you to give up on this. I want you to really develop your airflow troubleshooting and understanding of how it works in the system. So piece by piece, please, just take each little segment of what I've talked about, apply it, understand it, practice it for a few months, then take the next piece. Anyway, final questions. We got to get back to work. How's the format? How's everybody think about a webinar for?
Oh yeah, it's fun to watch.
Yeah. Peanut gallery. Any other questions over there going on? Anything we need to throw in here? Okay. Anything, last questions? I'm going to look right here what's fresh in the chat. You got seconds to put it in there, otherwise I'm moving on. I don't have time to scroll back through it all. Sorry about that. Pushing, try. I do highly recommend getting a belt tensioner tool. You know, if you don't have one, be great. Is a foot fetish the name of the tool to measure airflow? I've never heard that, so I'm gonna say no. I'm not honestly tool to measure airflow. Okay, yeah. Appreciate it, Sterling. You're funny. That's all right. Okay, well, y'all get back to work, get out of here, stop watching videos, get something done. We'll see y'all later.